Welcome back, everyone. I'm here on page 6 of the Chapter 1 outline, and we're going to be continuing from where we left off the last time. In the last lesson, we learned that errors are a fundamental part of all measurements, and we learned to differentiate between precision and accuracy. You also learned how to assess the number of significant figures in a given number. Today, we're going to continue learning more about significant figures. Specifically, you're going to be learning about how to handle significant figures when performing calculations. Here are some points to keep in mind as you learn how to do this. First, it's very important when you're performing calculations with measured values that you do not change the precision for a value. We don't want to make something more precise after a calculation or less precise. We want to keep the same precision through multiple calculations. How do we do this? Well, we will learn to maintain the integrity of precision by following some simple rules. To help you learn these rules, I've divided them into two different sets based on the type of calculation that you're performing. For example, first we're going to learn about handling significant figures when we're performing multiplication and division type calculations. After multiplication and division, we'll also look at handling significant figures when doing addition and subtraction. So let's go ahead and get started and learn how to handle significant figures when we're performing multiplication and division operations. For these type of operations, I call the rule that we follow the least significant figures rule. And what I mean by that is when we're performing a multiplication or division, we look at each term that we're multiplying or dividing with the other terms, and we assess how many significant figures are there in each of those terms. So, for example, we have a calculation here where we have 3 different terms being multiplied together. Our first step should be to assess how many significant figures there are in each of these terms. Let's go ahead and do that first. The first term, 80.2 feet, has 3 significant figures. The second term, 3.407, has 4 significant figures. And the last term, 0.0076, has 2 significant figures. Notice that when we multiply these terms together, we get a calculated value with many more significant figures than the individual terms themselves. If someone performed these measurements and then reported this calculated value as the result of those measurements, they would be incorrect because it provides a precision that is far greater than the measurements that were used to produce it. To fix this, we have to use our least significant figures rule. This is the rule that we use for multiplication type operations, and it goes like this. We round our calculated value down to the same number of significant figures as the term with the least number of significant figures. So in this example, we have 3 terms. We have 3 significant figures in one, 4 in another, and 2 in the last term. So how many significant figures should we round our calculated value to? If you said 2 significant figures, that's correct. We need to round our calculated value down to 2 significant figures because that represents the term that has the least number of significant figures. So let's go ahead and do that rounding. So following the procedure that we learned in the last lesson about rounding values, we start at the 2, that's going to be one of our significant figures, and then we go over to the 0 position and we say that's also going to be a significant figure, and then we have to look next to it. Now we don't want to have any more than 2 sig figs. That means we have to round off the rest of these values. Are we rounding up or rounding down here? Well, that's correct, we're rounding up because 7 is 5 or greater. So our rounded value here becomes 2.1. Now you might have noticed I left off the units for this, and we're going to be learning more about units in today's lesson. Note that we're multiplying feet by feet by feet. That means the unit for this actual number that we're getting at the end is cubic feet, or feet to the 3rd power. Now it turns out that we handle division operations the same way that we handled multiplication type operations. Let's look at this example to see how this works with division. We have 2 terms that we're dividing, 47.4 square feet, which is divided by 0.22 feet. So we have 2 terms. Let's look at the number of significant figures in each term. Our first term has 3 significant figures, and our second term has 2. How many significant figures should our calculated value be rounded to? That's correct. two significant figures. When our calculated value of 215.4545 is rounded, we get 220. And this has the correct number of significant figures based on this least sig figs rule. If you had to perform a calculation that involved both multiplication and division, you would still follow the same procedure. You would look at each of the terms, assess their number of significant figures, and then round your value to the least number of significant figures, which appear in the terms that are being multiplied or divided together. Let's go to the next page and learn about addition and subtraction type operations and how we handle significant figures then. When you have a calculation that involves addition or subtraction and the terms have significant figures in them, we follow a slightly different rule than we did for multiplication and division. I call this rule the least places rule. To use the least places rule for addition and subtraction, we look at the terms we're adding or subtracting together, and we assess the decimal place value that the least significant figure is in. After I know that, I have to round the calculated value, making sure that it doesn't exceed the precision of that least significant figure. Let me show you how to do this with an example. Here I have two terms that I would like to add together. Because I'm doing adding, I need to make sure I'm using the right rule. I'm using the least places rule here. The first step in using the least places rule is to look at the least significant figure in each of my terms. So for example, 24.1 has 1 as the least significant figure. Remember, the least significant figure is a significant figure with the smallest value, the smallest decimal place value. What decimal place value is that 1 in? That's correct, it's in the tenths position. Let's see if we can look at the next term and find where the least significant figure is sitting as far as its decimal place value. Which of those digits in 35.03 holds the least significant figures position? Well, that's correct. It's that final 3 in the number. Now we just have to figure out what decimal place value does that final 3 hold. That's correct. It's in the 100ths place. So that's the first step for using this least places rule. Just figure out what decimal place value the least significant digit is in. Now we go on to the next part of it. This is where we round our calculated value. Our calculated value needs to be rounded to the same precision as the term with the least precision. And I think that's where a lot of people get confused. Let's compare tenths to 100ths. Which of those is more precise and which of those is less precise? Think about this. 100ths. 100ths is more precise than tenths because it's a smaller value. If we were to measure, say, 100ths of an inch, we would need a ruler with much smaller markings on it than one that measures 2/10ths of an inch. So when we're trying to figure out what our calculated value needs to be rounded to, we pick the worst of those two things. Not the best, not the most optimistic, but the least optimistic. That would be the larger or less precise decimal place value. So in this case, we're talking about the tenths position. And that means our calculated value needs to be rounded to the tenths position as well. So the result of this addition should be 59.1. Now that you've learned the least places rule, this would be a good time to pause the video and maybe go do a couple of practice problems with addition, subtraction, and maybe even multiplication and division. You can find those in the problem sets that I have on Canvas for Chapter 1. So print that problem set out if you haven't already, and just try a few of the problems. Let's do another example together here with addition. Here we have 3 terms that we're adding together, 46.1, 8.357, and 106.22. We're being asked to circle the correct answer after rounding. So see if you can apply the least places rule for addition operations and get the correct answer. When you unpause the video, I'll show you what it is. So the first thing we should do is find the place value of the least significant figure in each of our terms. We have 1 in the tenths, we have a 7 in the 1,000ths, and we have a 2 in the 100ths position for the terms that we are adding together. So now we have to look at the different answers and figure out which one matches up with the fact that we're rounding this to the tenths position. That's where the 6 is. So we're going to be rounding this up, and B is the correct choice here. We're going to 160.7. So if you got that one right, great job. Let's do another example. Pause the video and see if you add together 8600 plus 1492 and 1776.74, if you can round the calculated value to the correct number of digits, given that we're dealing with an addition problem. When you unpause the video, I'll show you my solution. First, you need to assess the decimal place value of the least significant figure in each term. For 8600, we're talking about the 6. What decimal place value is that 6 in? That's correct. It's in the 100s position. 1492 has the 2 in the least significant figure position. And what decimal place value does that 2 have? That's correct. It's in the 1s position. 1776.74 has the 4 as the least significant figure. And what decimal place value does that 4 have? That's correct. It's in the 100th position. So what should our calculated value be rounded to? What decimal place should it be rounded to? Well, that's correct. We have to pick the least precise of our choices here. Which one of these decimal place values has the greatest magnitude? If you can answer that question, you know which one is the least precise. That's correct. 100s represents the greatest magnitude, and therefore that's our least precise term. We need to round this calculated value to the 100s place. Let's go ahead and do that. First, find the digit that's in the 100s place. Next, look to the digit to the right-hand side. Are we rounding up or are we rounding down? That's correct. We have a 6 in that position, so we're rounding up. What does this number become? That's right, it becomes 11900. So if you got that one right, great job. You're definitely on the right track. The only thing left for you to do is practice more of these. And I'll remind you again, the problem sets are a good source of additional problems. In the problem set, you're going to find I have examples where I mix addition, subtraction, multiplication, and division following rules of operations. I want you to go and practice those examples specifically because they add additional complexity on how you get to the right answers. And the only way you're really going to learn that is by practicing them. So now let's move on to the next page where we're going to start learning about units. So far, we've been focusing our attention on the numerical values of measurements and the errors that those numerical values can have. But that's not all there is to measurements. The other part of a measurement is the unit. Units describe the type of measurement that was taken and is being reported. All measurements have two parts. They have a value that expresses the magnitude of the measurement, and they have a unit, which is a label that explains to somebody else or to yourself later on what type of measurement was actually made. Note that measurements without units are meaningless. Without a label describing the type of measurement that was made, we have no idea what it means. It's just a number. Choosing the right unit to document a particular measurement will depend on many different factors. We will learn about two different systems of units that are available. The first system is called the SI system of units. The SI system was developed in the 1960s and is based largely in part on the metric system that we will probably focus more on in this class. It's important, however, to be aware of the SI system because we do use some of these SI units occasionally, and if you go on to engineering or other fields, you'll probably use these as well. The SI system provides a set of units that are divided into two overall categories. There are SI base units and there are SI derived units. The SI base units are also known as fundamental units. These are the building blocks of the whole SI system. All the other units, the derived ones, are in some way based on the SI base units. Let's learn what units are used as SI base units for different types of measurements. As we go through this table, we're going to learn about the unit name and the unit symbol. Measuring distance in the SI system, we use the unit meter, which has the symbol M. For mass measurements, we use the kilogram, which has the unit symbol kg. As you will soon see, kg, the kilogram, is actually a metric prefix, the letter K, in front of the metric unit gram. This actually means 1,000 grams, where the K stands for 1,000 and the G stands for grams. The kilogram is used in the SI system because of the large mass of many planetary bodies. In chemistry, we're usually using smaller masses than that, so we'll focus on things like the gram. Time. Time is measured in the SI system with seconds, and we give seconds the symbol lowercase s. In the SI system, temperature is expressed using the universal scale for temperature, which is the Kelvin. Now, you're probably more familiar with degrees Fahrenheit and degrees Celsius as a way to express temperature. Degrees Celsius is a temperature scale from the metric system, and we're going to see using that here in a few minutes. You'll also learn about how to interconvert those different temperature scales, Fahrenheit to degrees Celsius to Kelvin as well. Moving on, we're also going to talk about the amount of substance, and the SI unit for the amount of substance is the mole. You're going to learn that the mole is actually a number, kind of like the word dozen or pair. It's a word that means a number as far as a counting number goes. And you're going to see how we use the mole quite a bit in this class later on. For electrical current and luminous intensity, we don't often use that in this class, but the units for those are ampere and candela, which have the symbols A and CD. So there we have the SI base units. Now, what if we had to take measurements that did not fall into one of these simple categories? Say, for example, volume. Notice that volume isn't on this list, but we measure volume all the time in the lab. Well, that's where the SI-derived units come in. SI-derived units are units that we can derive from the SI base units. Theoretically, any type of unit that we might want to use can be derived from some combination of the SI base units. For example, area is described as a square meter in the SI system. The derivation of that comes from the fundamental units from the SI system for length, the meter. If we multiply a meter by a meter, we get a squared meter. For volume, the SI-derived unit is the liter. The liter is based on a cubic unit of length. If we multiply the meter by the meter by the meter, we get a cubic meter, and this is defined as a liter. Things like frequency can also be shown to be derived from SI base units. Frequency is a measure of how much something is happening per unit time, and the unit of time in the SI system is second. So if we're saying per unit time, we're really saying 1 over time, how many times per second. That's 1 over s, or s to the negative 1 power, and that's called the hertz in the SI system. There are other examples of this, say for example heat energy, which is called the joule, which is based on a combination of mass and length and time as well. So those are the SI-derived units. We're not going to spend a lot of time seeing how these SI units are derived. I just wanted you to know that's kind of how we can take this SI system and extend it to measurements that don't fit easily into this category that we've shown above. Now what we're going to do is go to page 9 of this lecture note outline packet, and we're going to look at the units that we probably use a lot more frequently in chemistry, those from the metric system. So let's go to the next page and take a look at that. The metric system is another system of units that we use very frequently in chemistry. The metric system is built around 2 core concepts. We have something called base units, which are the labels that we assign to different types of measurements. So these would be things like labels for mass, which happens to be the gram or the letter G. For length, we use the meter or m, and so on. The other part of the metric system are what are called unit prefixes. And this is the part of the metric system that I think a lot of people don't understand at all until they take this class. So it's something you're definitely going to learn as new if you don't have this experience already. Now, what are these unit prefixes? Well, they are symbols that we place in front of the unit label. This is why they are called unit prefixes, because they prefix the unit label. They come before it. Now, what do these unit prefixes do? Why are they there? Well, what they do is they scale the unit that they're in front of, either up or down, depending on if we need a larger magnitude number for that unit or a smaller one. And it turns out these unit prefixes scale based on a power of 10. We'll learn what those unit prefixes are and what their values are soon. But before we do that, let's learn first about the metric base units themselves. Many of the metric base units are identical with the SI base units, but there are some differences. Let's go through each of them in turn. For example, length in the metric system is described using the unit meter, which has the symbol lowercase m. For mass, instead of using the kilogram, the metric system uses the gram, which just has the symbol lowercase g. For time, we use the second again, which again has the unit symbol lowercase s. For temperature, we use the Celsius scale here, not Kelvin, and that has the symbol C or degrees C. For volume, we use the liter, which has the symbol capital L. And finally, for frequency, we use the hertz, which has the symbol Hz. Because measurements can be incredibly large or incredibly small, they have a very wide range of possibilities. To take this into account, the metric system was designed to allow for modifications of the base units by scale. To do this, we use something called metric unit prefixes. These prefixes are symbols that we place before the unit that they're modifying. In this way, a unit can be scaled up or down depending on which metric prefix is before it. Now, to use this system effectively, it means we need to know what are the metric unit prefixes, what are their values and names, and how do we actually take advantage of them. So that's what I want to show you here. We're going to learn about each of the metric prefix symbols that we frequently use, and we're going to learn what are their names, their symbols, and their values. Because we use the metric system so extensively, you need to make sure you know all this information as well. So let's go through the different names of the metric prefixes that we use, and let's write down their symbols and values. Note that this is not a complete list of all of the metric symbols. There are many others. I'm showing here the ones that we most often use and the ones that you absolutely need to know. Let's start here at the top of the list. The first metric name that we're going to learn the symbol for is the name mega. You might be familiar with this metric prefix if you've used computers. For example, you've probably heard about megabytes. The metric symbol for mega is the capital letter M, and this capital letter M stands for the metric value 1 million, which is 10 to the power of 6. Now, if you've heard about megabytes, you may have also heard about kilobytes. The metric name kilo has the metric symbol of lowercase k, which stands for 1,000, or 10 to the third power. So if we had a megabyte, we would have 1 million bytes, but if we had a kilobyte, we would have 1,000 bytes. Next on our list is the metric name deci, which has the metric symbol lowercase d, and deci stands for 1/10. So deci is a modifier that takes a unit and makes it smaller than 1 rather than larger than 1. The power of 10 for deci is 10 to the negative first power. We also have the metric name centi, which has the symbol lowercase c, and centi, like the word it's derived from, which is cent, means 1/100th, or 0.01. We can also write this as a power of 10 if we write 10 to the negative second power. If you ever forget what centi means, try to remember how many cents there are in a dollar. Now, I know lately these days not very many people use cash, but it's helpful to know that there are 100 cents in a dollar. If nothing else, it might help you with the metric prefixes. So if you can remember that a cent is 1/100th of a dollar, you can remember what the metric prefix C stands for. So as we see, deci and centi both modify a particular unit to make it smaller than 1, and this continues with milli. Milli has lowercase m as its symbol, and it stands for 1,000th. The power of 10 for this is 10 to the negative third power. So if you ever see the letters mm next to each other, that stands for a millimeter, which is 1/1000th of a regular meter. After milli, we get into unit prefixes that represent very small modifiers. The first of those being micro. Micro has a unique metric symbol that is based on a Greek letter called mu. The Greek letter mu looks a little bit like a U, at least to me it does. And micro, or mu, has a very small metric value. It's actually 1/1 millionth. So its power of 10 is 10 to the negative 6 power. Now you might see a parallel with micro and mega. Mega is symmetric with micro around the letter 1, meaning it's 10 to the 6 power, whereas micro is 10 to the negative 6 power. That's how I first learned mu when I was learning the metric system myself, as I remembered mega because of megabyte as being a million, and micro, which has the same first letter, M, is 1/1,000,000th, not 1 million, but a small million, or a millionth. That's how I remembered it. The metric symbols nano and pico are both very small modifiers. Nano, for example, with the metric symbol N, has a negative 9 power of 10. And pico with the metric symbol P stands for the negative 12th power of 10. So now that you have a list of the most useful metric prefixes for this class along with their values, what you should do is make some flashcards. And on one side of those flashcards have the metric symbols, and on the other side of that you want to have the powers of 10 and or the values that those symbols represent. I would do that as soon as possible, like right after watching this video, and you'll find you can learn those pretty quickly. You want to make sure you have those memorized before we go to the next lesson. And the reason why is in the next lesson, we're going to be learning how to interconvert different units. To do that effectively, you need to have a good grasp of these metric prefixes so that you're not constantly looking stuff up or are confused by the different steps that I'm showing as I go through those. So this can only help you if you go and memorize these as soon as possible. All right, before we end this lesson, let's go to the next page and just see how these metric prefixes work with a few simple examples. So to show you a few examples of how these metric prefixes work, what I've done here is taken a few of the metric prefixes we just learned and placed them in front of the metric base units that we also learned. And by doing this, we can see how they work. So in this first example, we're going to look at the metric prefix K, or kilo, and we're being asked which is larger, 10 grams or 10 kilograms. Now, of course, 10 kilograms is larger than 10 grams, but you might not already know that. And if you don't know much about the metric system, that would be confusing. Let's just break this down to its simplest elements and see what the difference is between 10 grams and 10 kilograms. The first thing to notice is that in both cases we have the letter G. That means we're measuring mass with grams in both cases. Now when we write 10 grams, we're not modifying the base unit gram with any prefix. It's just the unit gram. Because there's no metric prefix in front of the letter G, it's unmodified, and there's just a 1 there. So what we have is 10 times 1 gram, or 10 grams. Now what about 10 kilograms? Here we have the letter K, which is a metric prefix that stands for 1,000. So that means we're modifying the gram by 1,000. So what we have is 10 times 1,000 grams. And of course, 10 times 1,000 grams is definitely more than 10 grams. Let's go to the next example. Here we have 1 centimeter equals how many meters? Well, to figure out how many meters 1 centimeter is, what we need to do is get rid of that C, but replace it with what value it actually stands for. What does C actually stand for? Well, that's correct. C stands for the word centi, and centi means 1/100th. So what we need to do is replace that letter C with the number it means, and that happens to be 0.01. By replacing the letter C with what it stands for numerically, we can see that 1 centimeter equals 0.01 meters. So now that you've seen me do this a few times, I want you to pause the video and try this also for examples C and examples D. And I want you to look out for any possible errors that there might be in these examples. Hint, hint, there is one, and I want you to find what it is. So pause the video, and then when you unpause it, I'll show you my solutions. For the first example, we have 1 microsecond, and we want to convert that into seconds. To do that, we need to recognize that this micro symbol stands for 10 to the negative 6. So if we have 1 microsecond and we replace the symbol Micro with 10 to the 6, that would mean we have 1 times 10 to the negative 6 seconds, or we could just write 10 to the negative 6 seconds. If you got that one right, great job. Let's do letter D. Do you notice any errors with letter D? Well, that's correct. There's a capital K in front of Hertz. Now, unfortunately, capital K is not one of the metric prefixes. K actually stands for a base unit in the SI system for temperature. It's actually the Kelvin. For what we mean here, it's likely that K was supposed to be lowercase. And if it was lowercase, that would stand for kilo. Kilo is 10 to the third power. So if we replace kilo with 10 to the third, that would mean 1 kilohertz equals 1,000 hertz. Now let's do our last example. We have 1 and then the symbol P and then the capital L. What does all that stand for? That's right, we have 1 picoliter here. So liter is a metric unit for volume. It's also the SI unit for volume, and pico is the metric prefix that is represented by the letter P here. Now you might remember that the lowercase p stands for 10 to the negative 12th power. So we can replace that p with 10 to the negative 12, and we can find out that is equivalent to 1 picoliter. As a recap of today's lesson, we've gone through calculations and how we handle significant figures in those calculations, and we've also covered an introduction to the metric and SI unit systems. In the next lesson, we're going to learn a technique that will allow us to easily convert one system of units into another. This is called dimensional analysis. So thanks for watching the video. Please let me know if you have any questions, and I will see you soon.